So we have here a battery. Just to help you out, I flipped the battery upside down. We have a resistor, you're welcome, and we have a resistor, and we have our battery, and we have, I'm sorry, our resistor and our battery. We have, let's call this 5.0 volts. This is 2.0 ohms. This is going to be 4.0 ohms. This is going to be 6.0 ohms. And this one is 10.0 volts. Our goal, of course, is to figure out the currents everywhere. Okay, tell me, Nitish, something we need to pick.
Loops and their directions.
Loops and directions. So, we'll start with loop A. You should pick a direction for loop A. Counterclockwise, from in front of the board or behind the board. Was this loop going to be, this is just for an area vector, just for fun. He's chosen counterclockwise from you. Is that out of the board class or into the board? Out of the board. So, not that we describe them that way, but just why not? So, loop A, you should keep going.
Loop B is the other way.
We're going to have loop B going this way and loop C. Okay? This way, all the way around the outside. Loop C. We clearly have junction A and junction B. Let's have the current going through this battery. We'll call it current 1. Is that current up or down, Nitish?
Up.
Up. We have a current going the opposite direction through the battery. This is fun. We have the current in the middle through resistor 4. Current 2, we'll call it. Sierra, which direction, up or down?
Say down.
Down. This is fun. Current 2. Current 3. We'll go through the 10-volt battery. Emily, up or down? Up. Okay. So here's what I want from you. I want you, right now, to create 3 equations. One for junction A, one for loop A, and one for loop B. Don't solve them, just get them to the point where you have 3 different equations, and we'll talk about what we're going to do from there. Meg.
I know current 1 goes up.
I was asked the question, how do I know current 1 goes up?
You don't.
You don't.
That's why I kept saying it was going to be fun.
That's why I did. All right, Bill, junction A, current's going in.
Junction A? Okay, so I said current 1 plus current 3 equals, yeah, okay. Current 1 plus current 3 is equal to current 2.
I agree, we have current 1 and current 3 going into junction A and current 2 going out of junction A. Good. The potential difference around loop A. Flat.
Alright, we're gonna have a negative that E thing. Alright, wait, hold on. Negative delta D R 4.
Hold up. Sorry, I wrote down what you said, I don't know if it was wrong. Negative potential difference across resistor 4.
Plus the potential difference of resistor 2. Oh, that should be minus. And then minus that E.
That E thing, Dorsetter, what's it called? Electromotive force, or we could call it EMF. Jenkins.
He has all negatives adding up to 0.
I agree with that. Okay, let's start with this one. Start with A. As we go opposite the direction of the current through a resistor, does the electric potential difference go down or up, class? Up. Same is true here, right? So that's going to be positive. What about the potential difference across EMF 5? John?
Stays the same. It's still negative
It's still negative. Why is it negative?
because the current's going the other way from
The current direction has nothing to do with whether the EMF is going to be positive or negative across a battery. Sierra?
It's going from the negative to the positive.
It's going from the negative to the positive. Which class is the potential going up or down? Up. So here, we have all positives adding up to 0. Is that possible? What does this mean?
Screwed up.
It means one of our current directions is wrong. Is this a big deal?
Yeah.
No. Not a big deal. So we have 0 equals the potential difference across resistor 4. This is current 2 times resistor 4, plus the potential difference across resistor 2, which is going to be current 1 times resistance 2 plus EMF 5. In other words, 0 equals current 2 times 4 plus current 1 times 2 plus 5. Potential difference around loop B. Loki.
It's positive EMF at 10.
Okay? As we go this way across battery 10, potential go up or down?
It's down.
Goes down. We're going from positive to negative, so that's actually going to go down. So that is negative. Keep going.
And then positive potential difference at 6 for battery.
Resistor 6.
And a positive potential difference at resistor 4.
Again, we're going opposite the direction of the current, so the potential is going to go up, and opposite direction of the current, so the potential is going to go up. We have 0 equals negative EMF 10 plus current through resistor 6 is current 3 times resistor 6 plus resistor 4 has current 2 going through resistor 4. So 0 equals negative 10 plus current 3 times 6 plus current 2 times 4. Why is this problem more difficult than the one we did previously? Nick? The second one that I set up, we had 3 equations, but I set it up specifically so you could solve one and then the other and then the next one. Here, it's actually set up so you have 3 equations and 3 unknowns. So, you have to solve one of the equations for one of the unknowns, plug it into the other one, and then solve that one for the one unknown, and so plug that into the first one. Right?
Yeah.
Or you could do this. Let's rearrange this equation so that we have, let's see, current 1 minus current 2 plus current 3 is equal to 0. Let's rearrange this equation so that we have 2 times current 1, let's see, plus 4 times current 2 plus 0 times current 3 is equal to negative 5. And this one, we could do 0 times current 1 plus 4 times current 2 plus 6 times current 3 is equal to 10.
Wait, where did the last equation come from?
This one comes from here. And this is a what? A matrix. If you look, we can set up this matrix. We have 1, negative 1, 1, 0, 2, 4, 0, negative 5, 0, 4, 6, and 10. In order to solve this, what can we use?
A calculator.
Yes, a calculator. What are we going to use what function are we going to use, Nitish?
The row echelon, the reduced
Row reduced echelon.
What a champ.
So you need
was
to get out your
impressive.
calculator and plug in this matrix into your calculator and use the row reduced echelon form to get the solution to this. You need to create a matrice. that is a 3x4 matrix so that you can then plug this into your calculator and then use the row reduced echelon form. I want to know what is the equation we end with here? Or what is the matrix? 1, 0, 0, 0, 1, 0, 0, 0, 1.
Negative.
Second.
Is this right? But matrices.
I didn't get to matrices.
Second. Matrices. Right? And then edit. Okay. And then you can change your dimensions.
But this last cell right here too.
I don't know how to.
So it's a 3x4.
Oh, I found it.
Double, I'm sorry, double repeating it like so.
Honestly, I thought we would never have to do it. Use like a matrix, math, and go down to
That's what I got too.
and
Ladies and gentle people, notice what we have here is we've reduced a circuit down to something that you could solve using a matrix. Do you see the application of computers to circuits here?
Yes.
Right? That's what we're looking at. You are basically using a computer to solve for the various currents in this circuit. The truth of the matter is it doesn't matter how complicated this is for the computer. Really, I mean, there is a limit to it, of course. But this gets exceedingly complicated if you were to try to do this. I mean, if you think about it, if we instead had 5 loops, right? You'd have 5 different equations that you would have to try to solve simultaneously. Okay. So, here's how it's going to work as far as this class is concerned. You really need to make sure you know how to do this, because this is an important step, being able to use row reduced echelon form instead of going through and solving 3 equations simultaneously. If you're going to do this, you need to be able to show me all the steps that I've got right here, all the way to setting up this equation. You've got to identify that you're using row reduced echelon form. You've got to get to your answer, and then you have to check your answer. How are we going to check our answer here? Garrett.
Plug it back, or yeah, plug it back into the original integral.
What equation are we going to use?
I1 plus I2.
No, we're not going to go back to the current equation. What are we going to go back to? So,
Loop C.
we have not used loop C. So if we walk around loop C, give me the equation here for loop C. Nick?
It's EMF 10 volts.
Resistor 2.
Right now, plus potential difference of resistance. Resistor 2. Loss EMF of, is that 5 volt?
The 5 volt.
Yeah.
Again, so we're going in the direction of from negative to positive.
And then minus potential difference of the signal.
Why is it minus the potential difference across resistor 6? Jenkins.
The loop and the current are in the same direction.
We're going in the direction of the current, which we've already identified as a decrease in the electric potential energy and a decrease in the electric potential difference. So 0 equals EMF 10 plus the potential difference across resistor 2, which is current 1 times resistance 2 plus EMF 5 minus current across resistor 6 is current 3 times resistance 6. So 0 equals 10 plus current 1 is negative 2.045 times resistance 2 plus EMF of 5 minus current resistor 3, which is 1.81, that 81 repeating times resistance 6. I need a confirmation, please, that we get 0 equals 0 out of that. Please confirm, do we get 0 equals 0? Yes?
Yeah, you can't do this repeat.
Well,
So,
it comes very close, right?
0.0.
Right, that's fine. Okay, so now I need our answer. What is the answer for our various currents here? Emily, current 1.
It would be 2.045 going down through the battery cycle.
Keep going.
And then current 2 would be 0.227 going up through resistor 4. And then current 3 would be 1.81 amps going up through the
That would be our answer. So to review, you've got to be able to get 2 to 3 equations, set up your matrix, identify that you're using row-reduced echelon form, and show your equation, your matrix that has the row-reduced echelon form in it, and then give your answer. And finally, make sure to check your solution. Let me point out, please, that when you are doing this type of thing is not something you're going to run across on a multiple choice, right? They're not going to have you do this for a multiple choice. They might have you do part of it, like to set up just the loop across like one of the loops and come up with some sort of equation for that. But if they're going to give you a free response question where you have to do something this complicated, you will have your calculator and you need to show this specifically so that they know exactly what you've done, so that I know what you've done. Jenkins.
On a free response, like a question like that, would the checking part count for points, or?
That's for me.
All right.
I don't think that they would probably ask for that.
Yeah, because waste time.
But you want
That's
Running
for
out
me.
of time.
I'm saying I need
So
that.
on your test.
Absolutely.
All right.